Hi, my name is Simon Ilyushenko, and I would like to introduce to you Dr. Kevin Gurney from University of Purdue. He has impressive credentials. He has a bachelor's degree from Berkeley, 2 master's degree, and a PhD degree in ecology. He is on the IPCC panel, which has recently taken a Nobel Prize. He has given several congressional testimonies, including one recently for the Committee on Foreign Relations in the Senate. And he currently works at Purdue. He's assistant director of the Climate Change Research Center and assistant professor. And I probably can go on longer. The point is that he's doing work which I think is very relevant to all of us, and people working in Google doubly relevant. Because he runs a project called the Vulcan Project, which has started organizing information about the world carbon emissions, and he's trying to make them universally accessible, which should be familiar to Google when you put the problem this way. And from what I know, he has completed the most comprehensive and detailed inventory of carbon emissions of the United States, not just for individual sites, but for the whole country on as detailed level as possible using public data. And he plans to take this much further. So please welcome Dr. Gurney.
Thank you. Thanks. Put that there. So thanks, Simon, for having me out today and talking to you all. What I'll do is spend sort of maybe a third of this talk talking a little bit about carbon science, sort of carbon and climate, which maybe you don't get to hear every day, and then sort of launch into this Vulcan project and then sort of end up with something that might be a lot more familiar to a lot of you, at least I hope it is, I assume it is, and end up there. So a little bit of science and then some sort of technology and then some sort of mapping and imaging. So as Simon said, I've been doing this big project called Vulcan, and the sort of overarching sort of motivation for doing this project is really the recognition that across a whole bunch of disciplines, this is research, policymaking, governance, public organizations, there really is a need for global quantification of greenhouse gas emissions, but not just quantification in its zeroth order sense, but actually with a lot of space and time detail, and probably more importantly, something that's process-driven, that is emissions or quantification of emissions that are driven by the processes that make them happen, and do that in some sort of dynamical framework, in a potentially coupled framework, and I'll explain what I mean by that, and finally, obviously, something that's user-friendly and flexible so that we can engage not just scientists like me, but people within the business community, the public, policymakers, et cetera. So who needs something like this? I think a lot of people do, and I'm sort of in the upper, or I guess I'm sort of up in the upper right-hand sort of bubbles here. I'm sort of working in this area. I do a little bit of policy work, but I think all these folks need something like this, and I'll go into a little detail why. I'll first start with myself. I'm going to tell you a story about how I came across doing this work as sort of a carbon cycle scientist, and then sort of try to track around all those bubbles and explain each of those as well. So this is probably the most famous plot in all of geophysics. This is CO2 concentration as measured on top of Mauna Loa, 12,500 feet in the middle of the Pacific Ocean. Carbon dioxide concentration, of course, has a monotonic rise. No surprise there. We're emitting lots of CO2 because we're burning fossil fuels. It also has a very regular seasonal cycle, and that is a manifestation of the biosphere. That's nothing more than the planet breathing CO2 in and out seasonally due to photosynthesis and respiration every single year. So 2 big things, monotonic rise due to the combustion of fossil fuel, and a relatively even seasonal cycle due to the biosphere. But you can see there's actually interannual variability. If you were to take out that seasonal cycle, there's actually some little ripples in here, and those ripples hold an awful lot of information that we use to try to figure out what's going on. If you sort of back away from the global carbon cycle and put it into sort of big pots, it looks like this. The atmosphere holds currently about 760 billion tons of carbon in it. almost entirely as CO2, although there's some trace species. The oceans are probably the biggest reservoir other than rocks. Rocks, of course, have more carbon than anything else, but they're not part of the dynamical system. The oceans hold about 38,000 billion tons. The land holds about 2,000 billion tons, roughly half of which is above ground, half of which is below ground. And here we are, human beings, emitting in the 1990s on average something like 6 to 6.5 billion tons of carbon every year from the combustion of fossil fuels. We also emit, this is a very uncertain number, something like 1 to 2 billion tons every year due to manipulation of vegetation, primarily deforestation and primarily tropical deforestation. So all told, we emit about 8 billion tons into this big sort of circulating multi sort of pot puzzle. The atmosphere and the land exchange large amounts of carbon every year. As I noted in the previous slide, there's this regular seasonal cycle. And it is roughly these numbers: about 120 billion tons goes in, and about 120 billion tons comes out every single year, and actually an amazingly large flux of carbon. Something similar occurs in the oceans. About 90 billion tons every year goes into the ocean, and about 90 billion tons goes out. On net, prior to human beings interfering with the system, the biosphere and the atmosphere were almost in balance, and the oceans and the atmosphere were almost in balance. In fact, the whole system was, relatively speaking, in balance. There wasn't a lot of change in atmospheric CO2 unless you go back to times of glaciation. There wasn't a lot of variation. But we know by measuring in the atmosphere that we're raising its concentration by 3 billion tons every year. And if you look at this as sort of a checking account, if we're pumping in about 8, the atmosphere sees about 3, that means there's about 5 billion tons going somewhere else, right? 2 of that we now know pretty conclusively is going into the oceans. There's broad agreement on this. There's not a lot of mystery. Modelers, observationalists all agree about 2 billion tons going into the ocean. And the reason for that is actually something you all know very well, plain old Henry's law. Anytime you take water or any fluid for that matter, and a gas that's soluble in that fluid, and you increase the concentration of the gas above the fluid, more of it dissolves into the fluid. And that's exactly what's happening with the planet. We're simply pumping the atmosphere with more CO2, and some of it's dissolving into the oceans. There's probably a limit to that, but it's not too clear what that limit is. This still leaves one big piece of this puzzle, which is the piece that's motivated a lot of us to go out and do a lot of work, which is this last bit, which is if you take this into account, which we know pretty well, we take this into account, which you know pretty well, that into account, which we really know well, there clearly must be about 3 billion tons going into the biosphere every single year. And the reason why 20 years ago this was so surprising is the conventional wisdom was that the planet was actually getting browner. It was not getting greener. Turns out the planet actually is getting greener. That doesn't mean it's the type of green we like, because we are deforesting and manipulating vegetation. But in terms of just broad strokes, it actually is getting greener, to the tune of about 3 billion tons every year. It's been come to be known as the missing sink. Missing because it's not still clear why this is happening. It's still not entirely understood. We sort of know the magnitude now pretty well. We know roughly where it's happening. It's in the northern hemisphere where we live, but it's not entirely clear what the mechanisms are. So the reason why this is important, the reason why this has emerged as a very, very important scientific topic is sort of delineated by these 4 graphs. And these are a bit busy, and I apologize for that. But what this is 2 models. One is the red model, one is the blue model. These are big models of the atmosphere that have a carbon cycle coupled to them. So you have a big atmospheric model, it's got a big biosphere model, and the two can work together. And both of these models are driven by the exact same time evolution of fossil fuel CO2. So we're starting in 1850, going out to the year 2100. This is like a classic climate simulation that you've probably seen many, many times in books and in presentations. But these 2 different models respond very differently when you actually put a carbon cycle coupled to them. So now, fossil fuels go into the atmosphere, but the biosphere can react. It can either get greener, it can get browner, the oceans can react in different ways. And what happens is with these 2 models, 2 very different things occur. This is the ocean to atmosphere exchange. One of the models, the blue model, just keeps taking up more and more CO2. It just goes off into the future. We're pumping the headspace full of more CO2, and the ocean's just taking it up. The other model starts to saturate at about, 4 billion tons, about the middle of the 21st century, it looks like it hits a wall, and it just sits there. It takes up the same amount every year, but the amount going into the ocean does not increase. If you look at the biosphere, which is this, the exchange between the land and the atmosphere, there's a lot of noise, of course, because there's lots of interannual variability in the biosphere. The blue model, unlike what it did over in the oceans, gets to about the middle of this century, and it starts to flatten out. It basically stops taking up more CO2. It has a fixed amount and just sits there. The red model does something rather surprising, which has actually concerned a lot of people, which is that not only does it stop taking up CO2, but it turns around and becomes a source of carbon to the atmosphere. So no longer is it acting as a sink, but it becomes a source. So this is this feedback that a lot of people have been concerned about that actually has only been recognized in the last few years. Now, I can't tell you which of those futures is real. They're both possible. But clearly, this one is of great concern to a lot of people, because not only are we putting fossil fuel into the atmosphere, not only are we not getting help from the biosphere is now starting to emit CO2. And the broad reason for that is that as the planet gets warmer, microbial activity in soils everywhere around the planet starts to eat through all of the soil organic matter and oxidize it right into the atmosphere. The difference between these two models in terms of atmospheric CO2 is here, and as you can see, it's on about 50 or 33 to 50% of the total CO2 effect. Here's a difference in temperature, and it's also about 1/3 to 50% of the total temperature effect. So this is not just in the noise. This is a massive feedback that has serious implications. So that's sort of a motivation for why we worry about the missing sink, try to figure out where it is. Understanding the missing sink will teach us lots of lovely things about biogeochemistry, which is a lot of fun science, but this is really the punchline to a lot of people outside of science, which is if the missing sink were to saturate or weaken, which that red model shows, it would effectively double the amount of CO2 retained in the atmosphere. So it would basically make fossil fuel emissions look a lot worse than they are right now and have been for the last 20 years. It also has some serious implications for the Kyoto Protocol because it sort of mucks with the accounting in terms of the terrestrial biosphere within the protocol. So it's got a lot of political implications as well. So going back to the CO2 map, with our monotonic rise, our interannual variability, we can actually start to take a closer look at this map and begin to figure out where the missing sink is. And this is sort of a blow-up, or I should say, a more space and time explicit map of CO2. This is what we refer to as the magic carpet of CO2. It's kind of nice. It shows that wonderful seasonal cycle in the northern hemisphere. It's really big up where we live because we have a lot of land and a lot of trees up here. As you go down to the tropics, it has 2 cycles because of 2 wet and 2 dry seasons. And when you go into the southern hemisphere, the whole thing turns around 180 degrees in phase because the seasons are opposite in the southern hemisphere. It's also a weaker seasonal cycle because there's much less land in the southern hemisphere. So it's pretty cool. By looking at CO2 in the atmosphere, you can actually see a lot of what's going on around the planet. There's more information in this map. This is a model that we run at Purdue in my group that actually is a model of the biosphere. So what we do is we're pumping CO2 in and out of the atmosphere as plants grow. Here we are in the winter. CO2 is building up in the northern hemisphere. And as we go into the growing season, you're going to see this rapidly decline as plants leaf out and begin to remove all that CO2 from the northern hemisphere. And of course, that's the seasonal cycle. But the point here is, in addition to the seasonality, in addition to that gradient over latitude, there's lots and lots of space and time structure in the CO2 of the atmosphere. And it looks like weather, and it is weather. It's being pushed around by weather, but it's also being manifested by sources at the surface. And in the classic sense, it's a convolution integral of those two things, pumping away at creating CO2 in the atmosphere. So we actually attempt to use all that space-time structure as a signal and use it to figure out where carbon is coming and going. And we do that through an inverse process, and I won't bore you with all the details. I just put that. I know some people love to see mathematical equations, makes them very happy. I do too. But really all we're doing in this scheme is solving conservation of mass. That's all this is. This is just a conservation equation. Time rate of change of a thing, CO2, is a function of how it gets moved around and sources and sinks at the surface. Very simple. And this is a schematic of that. So we go around the planet, we measure CO2 in the atmosphere, and if we know the transport in between those points, if we know the flow of air, we can essentially solve for that. we can figure out what the answer must be. Where is the sink? Where is the carbon going? Where is it coming? Et cetera. Obviously, it's a very elaborate version of this sort of simple inversion schematic, but this is essentially all we're doing, solving for an unknown. Here are eyeballs on the system. If you look around the planet, this is actually right now where we measure CO2. Now, for those of us that do this, this is a very sad picture, because what this says is that for as important a gas as CO2 is, and it is supremely important, these are the only places that we routinely measure carbon dioxide. It's quite astounding. We basically don't measure it, is one way you could look at it. We hardly know where CO2 is. But these are our eyeballs on the system. We use measurements at all those locations, and again, with a gigantic transport model, we move things backwards, and we figure out where carbon must be coming and going around the planet. Now, important to this, which brings me to the real point of this talk, in a sense, is that underneath all of this, we assume we know fossil fuel CO2. We assume we know it. We know where it is, we know where it's coming from, and actually what we're doing is we're solving for the part of the problem that we don't know, which is the biospheric component. Because if you go back to those big bubbles, fossil fuel is a big chunk in the middle, and then there's the biosphere and the oceans. And actually, we try to remove the fossil fuel part and say that we actually know what that is and go after the biospheric part. So it becomes very important to know where all the fossil fuel CO2 comes from. In the old days, we knew it at very coarse scales. Nowadays, we need to know it at much finer spatial scales, and a lot of the reason for that is there's a satellite which is going to launch next month, which is very exciting because I've been waiting 3 years for this. It's going to launch next month, and it's going to measure CO2 from space, finally. So instead of having 50 dots around the planet, we're actually going to blanket the planet in CO2 measurements, and we're going to do it from space. NASA's launching this satellite. It's actually the Orbiting Carbon Observatory. It's going to measure something on the order of about 10 kilometers, okay, on the ground, which is much finer than we measure CO2 now. It's very exciting, and it's going to change everything we do. But in order to be able to avail of these measurements, it turned out we had to go back and figure out what the fossil fuel emissions of CO2 were much better than we knew them before. This is a map that all of us in carbon cycle science used to use, okay? It's you know, no surprises, right? These are the three big industrial bullseyes of the planet. The United States, Western Europe, East Asia, Southeast Asia, Japan, et cetera, right? Not a lot of surprises there. But if you look at this map, for the United States alone, this is what it looks like. This was the scale at which we had quantified fossil fuel, and this is much worse than it looks. Not only is it in 1 degree boxes, which are about 100 kilometers on a side, but actually we don't even really, we used to not even know that. We really knew what the total amount of CO2 was coming out of the United States, and we used population density to distribute that into these 1 degree boxes. So it was horrible. I would argue we barely knew anything. We know the whole nation, but when it gets down to like an individual state or even an individual county, no way. We had no idea. So we set out to actually improve this. So we went to NASA and we said, it's wonderful that you're spending all these billions of dollars on this satellite going up into space, but unless you do a better job of the fossil fuel, it's a big waste of money. And fortunately, they decided that was a reasonable thing to try to do. So that set us down this path of creating this thing called Vulcan, which I'm going to share with you now. Now, Vulcan is the Roman god of fire. A lot of people worked on this, including Simon, who introduced me, who's done some work, which I'll show you. Lots of folks at Lawrence Berkeley Labs here in the Bay Area, et cetera, et cetera. A lot of nice support from people out there. So we decided we've got to do a better job of this. How are we going to do it? And we took a very novel approach. Rather than doing what had been done in the past, we decided to leverage off of something that's already done, which is we monitor pollution like crazy in this country. Some people would say maybe not crazy enough, but we do monitor it, and we've done it for 40 years for local air pollution, carbon monoxide, and NOx, and SO2, and lead, and all those nationally regulated pollutants. So we looked at that infrastructure and took that information. Instead of reinventing the wheel, we decided, geez, we're monitoring all these local air pollutants. Why can't we use that to tell us where fossil fuel is being burned? Because anytime you burn fossil fuel, whether it be a car, a power plant, a factory, whatever, you make local air pollutants. And all that monitoring, it turns out, was utterly comprehensive. It had actually covered every single fossil fuel emitting source in this country. It wasn't convenient, and it took a lot of work, and it wasn't CO2, right? They're not monitoring CO2. Nobody does that in the United States. We monitor the nationally regulated pollutants. We'll probably be regulating CO2 in the coming years, but not yet. So we took all these pollutants, and in all these different sectors, we did lots and lots of stuff at different resolutions to try to downscale all that information and create a map that was a lot better than the one you just saw. And we like to think we've done that. This is just a little downscaling schema. I won't waste time on that. This is what it looks like. This is our combined commercial and residential sector. These are CO2 emissions in funny units. They have to be logged because the spread is so big, but much, much, much more detail. We're down now in this map down to 10 kilometers on a side, and we do this every hour. Now, we've done it for the year 2002, but we're planning on marching that forward in time. So a lot of detail. We've done, this is electricity production. These are basically all the power plants in the United States. This was not such a mystery. You know, everyone knows where these are. But we've done all the electric producing power plants. This is the industrial sector. So these are basically factories. Anything that burns fossil fuel to produce something is in this map. And in some cases, we have to spread things over an entire county because we don't have information about the exact geolocated point. But most of these are actually geocoded. It's a building, and we know where the building is, and we know how much CO2 is coming out the stack of that building. We've also put them onto roads. So we have all the mobile emissions in the United States placed onto US roadways by merging it with the GIS Road Atlas. The green dots are all the airports in the United States. We know how many planes are coming and going. We can quantify those emissions as well. This is sort of a movie. It's a little washed out, but the idea here with this movie is that it shows the peeling out of the time zones across the United States. So we're actually able to also not just quantify everything, but do it nicely in time and show that parts of the United States wake up before other parts of the United States. And this is very important for people that are going to drive an atmospheric model, because you need to know very specifically in space and time when CO2 is being emitted into the atmosphere. You won't get an accurate assessment of CO2 as it is in the atmosphere. So we've actually taken things and run it through an atmospheric transport model. And this is a model called RAMS, which we run in my group. And we have driven the RAMS model, which is a very elaborate mesoscale atmospheric transport model, with our CO2 emissions. This is an isosurface of CO2, and you can see a big warm front there. You see this interesting bleed out of CO2 down to Mexico, which is a manifestation of actually nearshore winds in the LA basin. Lots of interesting blobs of tunneling thunderstorms in the Midwest, et cetera. Lots of exciting action, and of course, all this blow off of CO2 over the Atlantic Ocean and over to Europe. Right? CO2 travels around the planet now as it's being emitted from everywhere. So this allows us to do lots of really interesting and fun science, which I won't, again, bore you with, but lots of neat things can be done with that. We put this actually up on YouTube, and within the first 72 hours, we had 200,000 views, which I know is not a very impressive thing at Google, but you have to understand, for nerdy scientists like me, that's kind of astounding. We're not Paris Hilton, right? But it was pretty amazing, and there was a lot of interest generated by this, and lots and lots of feedback and people interested in what we're doing. So we've also been evaluating it compared to the national totals that come out of the Department of Energy, and we do very well. Little bits of differences here and there, which we're always exploring and worrying about, but generally speaking, we do pretty well. We're going to do Canada and Mexico. We're in the process of doing Canada and Mexico because our goal was to actually do North America. We got a lot of nice press. This was actually a Sunday edition of the Boston Globe, so some of the old media picked up on it, New York Times, Wired, et cetera. Tons of blogs and new media picked it up. We had so much traffic actually to access the data that it brought down our server, which again is not a very impressive thing here, but was a little surprising to me because I really had no idea that there would be as much interest in this as there was. But clearly a lot of people were interested in this information other than scientists like myself. I had emails from just about every corner of the planet, more than I could ever respond to. So we've now, with Simon's help, been gearing up to put this onto Google Earth, sort of an obvious thing to do with something like this. It's got a lot of rich information. Our first cut at it, which I think is nice, is in every county and every state, we can pop up a pie chart which says how much CO2 is coming from the different sectors in your county, in your state. We can do it per capita, et cetera. So a very rich amount of information that we can put in people's hands, which I think is really neat. And I think right now we'll probably get this all wrapped up in January and have that out on Google Earth. We've also started to do a bunch of other things, which is, analyze things per capita, bring some socioeconomic data and mix it with CO2 to sort of make it a little more meaningful to people other than carbon scientists. This is just an example. This is actually on Senator Lugar's website now. They were really interested in it, and they put it up on their website. As Simon mentioned, I did some testimony to Senate Foreign Relations back in April, and I was there talking actually about deforestation and climate. But Senator Lugar surprised us in that he showed up with a map of Vulcan and was very excited about it, and made a very nice statement. And I highlighted it because I actually think it is a great indication of one of the powers of this type of information, is that as we go into a carbon trading market, which I would argue is almost inevitable at this point, something like this could become a crucial element in actually operationalizing carbon trading. To trade something, you got to quantify it, and you got to quantify it with reasonable accuracy, right? Nobody buys a stock that's $1 plus or minus $10. No one's going to buy that. It's got to be $1 plus or minus $0.0001. So we like to think that Vulcan has a role to play far beyond what we had initially set out to do. Right now we're doing an interesting thing, which is improving the traffic part of Vulcan. We've gotten data from over 20 states, traffic count information at individual locations, thousands of data points. We're actually talking to Navtech, who are the people that drive around in the cars and GPS everything, right, and put it onto Google Maps, about the 100 cities that they blanket with traffic monitors. Because believe it or not, a lot of this data, when we contact State Department of Transportation, they send us analog information. They sometimes don't even have it digitized. So we have to sit around digitizing books that thick of numbers. It's just unbelievable. But a lot of this information is not digital, or at least not available to us in a digital form. So incredible amounts of labor, but interesting things are coming out. This is a classic sort of data element. This is a rural location in Utah. This is a weekday. This is all traffic at an individual location. And you can see, because it's sort of rural, it doesn't really have a little bit of a rush hour, maybe you could argue, in the early morning, but sort of has this broad hump that basically when people are awake, there's some commercial business probably traveling out in this rural highway. It peaks in the middle of the day, declines at night. You go to the weekend at this location, and this is what it looks like, which at first when I saw this, I was completely baffled. Does anybody know what might explain that? Any guesses? Church. I mean, that's my explanation. I don't know, but I'm assuming this is church service. People are rushing off to church and then rushing out. And they're doing it for a morning service and a midday service is my guess, because this is on a Sunday. So really neat. And so we're taking all of that information and actually going to put it in so that our traffic, our CO2 emissions from our traffic, has all the fidelity of all the rush hours everywhere in the country. Instead of right now, which is sort of a coarse sort of climatology of driving patterns, we actually want to dial it right down to directly monitored data everywhere. Here's another idea. We're going to propose this actually to the Geo Challenge, which is due, I guess, in a few days. This is this flu trend website that has, real-time tracking of flu trends in the United States. Normally, this map has a lot of differentiated colors when the flu trends are different in different places. And sort of we want to do something much like this for CO2. We want to actually start bringing this so that you can dial out the actual trends in CO2 in almost real time, state by state. And believe it or not, you can do that because though it has never been used, the DOE produces in incredible detail petroleum, natural gas, everything you ever wanted to know about fossil fuel sales and quantities all over the country, week by week. and subweekly. They put these out in these reports because they're all interested in spot prices and trading, and it's all about fuel and all about trading fuel. And we think we can use this information and actually make a product that looks much like that flue trends for CO2. So again, building off of the platform that we've built, by adding some bells and whistles, we can actually create, I think, some really neat things. So stepping back again now, so Vulcan, has been a relatively successful product for science, but I would argue that actually to satisfy all of these people, we need to actually take a step beyond. And I believe to do that, we actually have to go even into finer detail and downscale this idea even further and actually change the way we do it. Instead of delivering this out to the public, we need to engage the world as data providers and data ingesters at the same time. Which means we've got to create a system that interacts with many of these communities, interacts with the public, interacts with industry, interacts with policymakers, et cetera. So to do that, I'll show you the all-familiar Google Earth zoom in. We've named this project Hestia. Now, Vulcan is the Roman god of fire. Hestia is the Greek goddess of the hearth fire. I'm lousy at acronyms, so all my projects have, I use Greek mythology or mythology in general to name all. So I have Terra, Hestia, Etna, Vulcan, et cetera. So what we want to do is take the Vulcan idea and bring it right down to, the classic building 3D Google Earth data layer. We want to bring it right down into this landscape, right? So emissions down into buildings, down into roadways that are right in a recognizable landscape that everyone has access to and in as close to real time as we can make it. So really dial up the specificity and the fidelity of this information. And I think that this has a lot of power for the policymaking community. Right now, as probably many of you know, there are, there's, more bills now bubbling around in Congress about legislating greenhouse gas emissions. This is not a new topic, but nothing's happened yet. But I imagine with the change of administration, that's all going to change. And we're going to have probably some sort of national level legislation. There's, of course, Kyoto, which is out there, and the rest of the world is moving on without the United States, but it looks like we may re-engage. There's also lots of independent U.S. action. There's the northeastern states have created a trading market amongst themselves. I think it's 9 now. There's cities all over the country that have taken on greenhouse gas mitigation targets. This one probably has, for all I know. Obviously, in the state of California, there are state-level targets, which are pretty aggressive. There's a Supreme Court ruling which said to the EPA that greenhouse gases are, in fact, in your bailiwick. They are not outside your purview. They're perfectly reasonable to include in regulations. And then finally is this U.S. cap, which is a consortium of, it's now 20 or 25 large industries that wrote a letter to the president saying, please regulate us, which a historian told me the last time that happened was in the middle of the 19th century with the rail industry. But pretty unheard of for a bunch of big companies to ask to be regulated. But they did. And the reason they did is that they're actually worried about the scatter of legislation that actually might make their lives harder rather than easier. They would rather one system instead of potentially a bunch of different systems that are different in whatever state you're in. And since many of these big entities obviously are not just across many states, but across many countries, this is a potential headache for them. So they have basically asked that legislation happen and happen sort of coherently at the national level. Here's a map of all the cities. There's many, many more now. So I would argue that right now, prior to Vulcan and prior to building Hestia, policymakers really have this sort of blunt instrument. In other words, they don't really know where the emissions in the system are. And they don't know in a lot of detail in space and time where they are, why they are, and when they're happening. And so we want to give them this, really a scalpel instead of this hammer. And the policymaking community, I think, really needs fidelity is the biggest thing. Because in order to get smart, efficient, economically viable policy, all those things we all want, you do need a lot of fidelity. You need to know what it is you're going after. Right now, the sort of canonical wisdom was, well, just regulate power producers, right? They're big, giant point sources of CO2. They're kind of obvious. We all know where they are. It's only 40% of US CO2 emissions from fossil fuel. And in many ways, there may be a lot of other low-hanging fruit. I mean, we all know it, and we've known it for 30 years, right? Energy efficiency, et cetera. And we engage in a lot of it, but from a policy point of view, the wisdom thus far is, well, we should just regulate power producers. I would argue that's fine, but you're missing a big part of the story. Regional and local managers who are going to be the people that are going to operationalize this, because even if we have national regulation, it always comes down to some local county manager or somebody on the ground in a county that's going to have to do this. They're going to have to go out and either count up where all the CO2 is and operationalize some policy that then gets sent up through the state and up to the federal EPA. And so these people need lots of information. And this is where they need a lot of what I would call sort of technical information. Obviously accounting, no big surprise there, but the ability to assess and the ability to build scenarios, to play games with their world, right? To play a computer simulation and find out, well, what if we change out the traffic lights with LEDs? What if everyone's driving a hybrid car? What if everyone's doing this? What if houses are doing that? And find out where in the system the fidelity is and where the soft spots are. And of course, everyone needs verification, no surprise. So the public, I think, has a big role to play. And I would argue, I remember when the first time I got interested in the climate change problem was 1981, over in a classroom across the bay in Berkeley. I was sitting in a class, and somebody gave a lecture on climate change, and I said, that is what I want to do. But I would argue that even in the intervening period, which is now almost 30 years, but even longer, climate change has always been a very difficult topic to communicate to the public about. It's relatively abstract. We talk about global mean temperature, which means almost nothing to all of us, because we don't live in the global mean, we live in a place. And in many ways, it's been very difficult to create any sort of transcendent imagery or conception of what this problem is. You know, we've had pictures of polar bears on icebergs. I mean, I guess that's the closest we've gotten. Maybe we have pictures of, you know, the temperature profile or the predicted temperature profile. But I would argue, actually, we've had a dearth of imagery. We have nothing that really transcends the reality of this problem into people's everyday lives. And I think it's been an incredible barrier to people doing anything. When I first started out doing science, I actually worked for a few years on ozone depletion. That was, I started out as a chemist, really. And this is a picture of the Antarctic ozone hole. This was on the cover of Time magazine. And up until the late 1980s, when this image showed up, you could argue the exact same thing was happening with stratospheric ozone depletion. Yeah, people talked about it, but it was this abstraction. It's down at the South Pole. Who lives there? What is this? A lot of confusion until this image showed up, until people saw on the cover of Time magazine a satellite image of the problem. And it changed everything. I would argue, circa 1988, 1989, the problem changed. It fundamentally changed. We had legislation in rapid fire after this. It essentially reframed it. It completely reframed it from something that was abstract and a bunch of nerds worrying about to something that could actually affect your life every single day because you might get skin cancer or whatever. So I call this a transcendent sort of policy convergent moment, and I think we need the same thing for climate change. And one way to do it, again, is maybe to utilize the infrastructure we already have, both through online visual mapping and imagery, and now the new fidelity we have on emissions. So this is actually a picture of my neighborhood here. This is my house, a little bit old. But I think what we can do is place, again, through Hestia, place the information right into people's neighborhoods. And you can do things not only quantify CO2, but show what would happen if traffic changed, if you're driving hybrid cars at an intersection, ethanol, whatever. You could do it in terms of dollars saved, carbon saved, whatever you want. All the metrics that we already calculate, we just don't do in space and time detail. We can layer right onto this image and bring this right into everybody's living room. You can do it for an individual house, maybe swapping out windows, changing the insulation. But the idea is to bring climate change into the living room of everybody and leverage it off a platform that everyone's now pretty familiar with, Google Earth or online mapping systems. So I'll mention a few attributes of the system, then stop and let you ask some questions. So there's a bunch of attributes that I think of when I think of Hestia, this system. First of all, it's methodologically consistent. And let me tell you what I mean by that. Right now, there's a lot of work being done on carbon footprinting, right? Everyone's doing it. Towns are doing it. Businesses are doing it. It's like a cottage industry, right? There's a bazillion little websites that tell you how to calculate your carbon footprint, which I think is a great thing. But I would argue, however, that in order to really do this, that's kind of not the way we should be doing it. Not that everybody shouldn't be involved. I do think they should. But we've got 20 methodologies. We've got everybody doing it differently. It's great for giving people a little bit of information about where they stand, but it doesn't connect upscale. It has no scale transcendence because it can't really be compared to anything at the national level, can't be compared to the state level. Again, everyone's doing it differently. As a scientist, I look at all the differences and it completely worries me because, frankly, I don't trust most of it. So I think we have the opportunity to at least build a system that is at least internally, methodologically consistent and is built from science first and then engages everybody to become involved. We can build a two-way data structure. So instead of just supplying this to the world, we could actually have people supply us with information. Right now, I cannot get the electric bill of everybody in the country. That's against the law. The utilities won't give it to me. And frankly, I might be uncomfortable if I was told all my billing was being sent to somebody. However, I should have the opportunity to donate that information if I want. If I had a reasonable sample of all the electric billing and all the gas billing of people across the United States, I could do incredible things with it. So we need to build something that is true two-way data structure, that is sort of a real modern Web 2.0 idea where people become part of the scientific infrastructure. They're supplying information and being a part of it just as much as we're a part of it. It connects grassroots to the world. That's the scale transcendent idea that things at the grassroots level now talk directly to things at the global level because the problem can now be connected. We have carbon cycle budgets at the planetary level. We've got them right down to the individual building level. National goals can be connected to local action. I would argue it's much more efficient to do things this way rather than have every industry go figure out their carbon footprint and redundantly do this problem over and over again. We should just do it once and do it really, really well. You could do cool things like compare different cities. By that I mean this will offer people the opportunity to build context, right? Everyone wants to know, how am I doing in terms of my carbon footprint, but how's my city? How's my neighborhood? How does it compare to the next city? Is there a reason why it's different? Should Chicago and Indianapolis have similar emissions? Should they be the same per capita? Maybe not. Maybe Chicago's colder, maybe they have older buildings, et cetera. People should be able to have complete, full context of the emissions and the things that matter to them. And I have this dream of people, showing up at city council meetings with this information in hand and requesting mayors and city councilmen and women to actually do something because they're empowered with the information. They've already quantified it, they know what's going on, and it's all in vivid detail in the communities in which they live. It opens up the possibility that everybody can trade carbon. We can trade carbon at much finer scales with higher fidelity, which could mean a more efficient trading market. Obviously, there's lots of assessment verification. And of course, this visualization is key. It has to be visual, and it's got to connect not only the essence of the problem, but it's got to connect it to the solutions. So within the landscape, not only do we have emissions, but we have all the opportunities whereby emissions could be reduced. And finally, I would say this is not really just an exercise in downscaling, which sometimes scientists, that's their first reaction is, okay, we're just downscaling stuff, right? I would say it's not downscaling. It's actually eliminating scale. Scale should become utterly and completely irrelevant. There shouldn't be local and global. It's just scale independent, right? This problem in its essence is scale independent in a sense, and we need to both quantify it that way, visualize it that way, and think about it that way. So finally, to sort of stop, I would say our first stab at this, Vulcan, is here. We're working on improving it, making it better, more accurate, et cetera. We're doing lots of fun science with it. Our goal right now is to make it accessible beyond just our community. Open this up to people, let them look at it, play with it, use it in whatever ways we can, make it useful. And ultimately, we want to do the world. So we want to take Vulcan and actually do the rest of the planet. Hestia, the finer detailed, building level, full gory detail concept. We've actually doing a pilot on the city of Indianapolis. They're kind of a guinea pig because they're nearby the university, big enough so they matter. We want to build this sort of Web 2.0 idea where we actually engage people and allow them the opportunity to come into the system, supply us with information, QA, QC it, and use it in various ways, and then deliver to them, in turn, a very powerful piece of information that gives them all the context they need. We want to try to get it as close to real time as possible. It's going to require a lot of stuff to do this in the type of detail we want. Clearly, satellite remote sensing is going to be at the core of this. There's no question to do this outside the United States, you have to use remote sensing. We don't have information like we have in the US everywhere around the planet. We need data, 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 and lots of visualization. And yes, ultimately to try to actually do the world, to try to not just do the United States or even Indianapolis, but actually attempt to do this across the entire planet. And obviously to get from here to there, there's a lot of things that have to happen, but I think technically there's no reason why it can't happen. And given the magnitude of the problem, which we've been talking about now for 30 years, to me it's actually quite surprising that we haven't done this. That's probably what's more surprising to me than how difficult it is to do, is that we haven't done it. We haven't even really tried. And I'm sort of floored by that. I mean, I forget about it, but when I step back from this problem, it's actually surprising that we haven't really gone and done this when we really should. So at that, I'll stop. Thanks again, Simon, and hopefully a few minutes for some questions.
Thank you. If someone has questions, please step by to the mic so people can hear you. If you're in the remote office, unmute and ask your question.
Oh, you have to go.
So I had one scientific question about, have there been any experiments at a micro level to see whether the biosphere can become a source of emissions, as with the way one of those scenarios might play out?
Yeah, I mean, there's a lot of so the classic one is soil incubation, right? Take a bunch of soil and heat it up, and what does it do? And yeah, CO2 comes out of it. When soil gets warmer, microbes are awake longer during the year, and they do start to work through soil organic matter. But at the large, this is the problem in sort of global ecology, is it's really difficult to connect individual plot sort of experiments and sort of extrapolate that across the planet, just because the biosphere is so heterogeneous. It's just so different from one place to the next, right? It's the classic kind of, everywhere you go is different, and it's profoundly true in the biosphere. And so while in-lab studies certainly show that as you warm up the planet, you have CO2 coming out of soils, the problem is that sometimes plants will actually start to photosynthesize more. So if it gets warmer, some mid-latitude or even high-latitude plants, they actually like warmer temperatures. In the tropics, they're usually near drought stress, but in the exotropics, they're happy. So it's actually a balancing act between more CO2 coming out of the soil and actually more CO2 going in it through photosynthesis. So it's a subtle balance between the two. And of course, where the balance lies, which direction, changes whether something's a source or a sink. And so actually understanding that very delicate balance between the two is what's so hard at large scales, which is why, at least right now, models are the only thing that have really been able to sort of look at this question at the large scale. People have done it in greenhouses and in incubation studies, but over larger scales, there's sort of no other way to do this other than models right now.
The data you have on your website, the download, is that comprehensive? Is that all the data that's being used, for example, in Earth now, and or is?
Yeah, so the stuff that we have that you can grab on the website is not, again, very friendly right now, right? We just sort of put 100 gigabytes of gridded hourly emissions up on our website for people to pull down. And again, the only people that are pulling that down are people like me who are interested in running a atmospheric model. But we are trying to sort of move towards more bite-sized bits of information that are useful to people outside of my community. And obviously through Google Earth, we'll be able to serve up some data. Actually, the research Google site, we're going to serve up the data. Right now, we have just the CO2 information rather than the underlying source data, although we point people to that because we don't generate that. It comes from the EPA, it comes from the DOE, and we definitely point people to that. But I think the goal for us right now in the coming months, in my opinion, is actually to make the data more digestible to people outside my world, to make it in smaller packets. We'd like to have the website serve up data on the fly in smaller pieces so people can zoom in on a map and yank stuff off rather than having to digest the entire 100 gigabytes of the data files. So we're sort of in the midst of making this better than it is now.
Okay, thank you very much. Thank you to Dr. Gurney.